So we need this prison population information about the females and the totals in there. I'll look at that. Wow, this really messed up. Okay. Using that one today. Yep. Alrighty. So, like I said, and we were smack dab in the middle of some stuff I wanted to show you, and I just decided hopefully you wouldn't be clearing a lot of stuff out. If we do have to re-enter it, we have to re-enter it. So we're still sticking all of our objectives, and we have set up models to represent real-world phenomena using numerical, algebraic, and graphical methods. We're really not truly through all of that yet, because we still need to talk about those graphical. And then combine those methods to solve and verify solutions. Hopefully we'll get into a little bit of that today. So we were Galileo's gravity experiments. So if you need to re-enter this data, we use list 5 and list 6 because we have a lot of other stuff in there about prison populations at that point. And I think we were able to see the scatter plot, but I really wanted to show you how to get that quadratic of best fit to graph automatically for you. Let's just ran out of time. List 5 and list 6. Anybody need more time? Get those two lists in there for the Galileo. Alright, so what we did was we said if we want to see this, we want to see all those dots and see what model would best represent this, we were going to have to go into second stat plots and make sure that one of these got turned on. So number 1, and then while blinky's over the top of on, we hit enter. And then we had to make sure that the lists that we put the information into were the two lists that were used for X and Y. And then just like we did with any scatter plot before, we had to change the window, and that's because this stuff was not anything. So Zoom 6 was not. And it was looking like that. And we hit graph. And we had that. Now, we cheated yesterday and just went into Y equals and typed that in. And for this one, that's not such a bad idea because it's a pretty easy little equation that we got. But what I want to show you is, because some of these become really nasty decimals, how we could get the calculator to put that equation in there for us so that we don't have to do that. And that would be under stats, calculate, and then we had said it looked like a parabola, so we went down here to quadratic regression, number 5. And now we have all kinds of different models of calculators out here. So my old yellow ones that have old yellow ones, what you're going to have to do is type in, yours will say quad regression. You're going to have to type in list 5, comma, list 6, comma, and then hang in there for a second while I go over the other calculators. Because we have to make sure those are the two lists that we're using. Now, I'm not worried about frequency lists there. What I want to do is I want the calculator to store this for me. So I'm going to go down to store and I'm going to ask it to put this in Y1. So what I have to do is figure out where are the variables in this calculator so that I can make that Y1. And they are right here where it says bars. So the old yellow calculators, you should be right here. Everybody else, we should be right here at store. And we are going to hit VARS. And we're going to go find Y sub 1. So I look up here at the top and I see those Y variables. I have to click over once to the right. And sure enough, I can graph functions, which is number 1. And look at that, I can choose from which y I want to use. Well, I just want y sub 1. And I hit 1. And when I calculate this, the calculator doesn't just do the regression, it stores that information for me in y sub 1. So if I hit y sub 1, I didn't have to type anything in. The calculator automatically put that in for me. And now when I hit graph, I'm going to see my parabola of best fit going over the top of my scatter plot. So very nice feature of the calculator to get that y to hold in there, especially when we get nasty decimals. This one.
Yeah, I get R on there for the calculator.
Oh, we didn't do that yesterday, did we? Yeah, if we want to see the r squared or the r, when you clear your calculator, it turns off the settings that let you see that. And r squared is great, but we're more interested in r, which is the correlation coefficient. We actually have to go into your calculator's catalog and turn it on. So we have to go into second 0, because that's where the catalog is. And you're going to scroll down until it says diagnostics on. And then you're going to hit enter twice. I'm not going to scroll down because this thing takes all day to do that. But scroll down to diagnostics on and hit enter twice. And once that's on, until you reset your memory or you take your batteries out, it will give you the R squared and the I from now on. So, all the way down to diagnostics on, hit enter twice. It should say done. And then if you redo the quadratic regression, you'll see the R squared. Everybody okay? Anybody need more time to get that stuff done? All right. Because that, again, gives us an idea of how good our model is. And R squared of 1 means if we take the square root of each side to get that correlation coefficient, we get a perfect 1. And 1 and negative 1 are perfect correlation. It means it totally matches whatever it was you were graphing perfectly. In this case, our parabola went through every point. Absolutely perfect. That is really rare. It does not happen a lot. We hope for a high value for R that's really close to 1, but rarely do we see it work out perfect like this. So now we've got a little bit more reading on the bottom of that page, and then we can get back to calculator use on the next page. So this says this insight led Galilei to discover several basic laws of motion that would eventually be named after Isaac Newton. While Galileo had found the algebraic model to describe the path of the ball, it would take Newton's and Leibniz's calculus to explain how it worked. So it was start. It was getting people thinking what's going on with gravity and how all of this works. It took a while for them to come up with all of this, but when you think about when he was alive and when he was calculating this is phenomenal. That he was interested in these things. Next up, fitting a curve to data. Well, we just did that. Exactly what we did. We showed an example too that the percentage of females in the U.S. prison population has been steadily growing over the years. Model this growth graphically and use the graphical model to suggest an algebraic model. All right, so we want to see what the dots look like and ask ourselves, parabola with this one, or maybe this one's a line. Maybe we should do linear regression. Maybe it looks like an S-curve. What does it look like so we can figure out which model would be best? So we've got our stuff still in there. Hopefully, do I need to go back to the prison population stuff? Is everybody got that okay? Okay, good. So we're going to make a scatter plot using list 1 and list 4 data that we saved from example 2. That was about those percentages. So it was years and then it was percentages. So let's get back in here and take a look at that data. So list 1. We had our years since, what was that? 1980. And then list 4 was when we figured out the percentage that we're going to be females because they want us to talk about whether or not that was increasing, decreasing, whatever it was doing. So now what we want to do is a stat plot of that data. So I need second stat plots, still turn on, number one, but now I'm using different lists. It's not list 5 and list 6 anymore, it's list 1 and list 4. So I have to hit second, number 1, get list 1 to show up. Go down to the next one, second, number 4, so list 4 shows up. And then, again, I'm thinking immediately, okay, my window has to change. This isn't the same data that I had in there. So for my window, let's see. If we start with our x's, we have 0 to 25. So I don't know, maybe negative 5 to 30. So I'm sure we can see all of that. And I took the 0 and tried to take 2. 5 ones. But now our y's were percentages. So what should we use for limits for percentages? 0 to 100. You know, makes perfect sense. If we want to see a little below 0, we could certainly put like a -2 or something in there. That's a pretty good window. And there are some spots in your notes there to fill in what are we doing with the window. But let's make sure this is going to show us all our nice points. Let's hit graph. And actually, I'm going to have to turn off my parabola. Y equals here. Come on. And it looks like that. So now, our 0 to 100 doesn't look like that was working too well. And that's because what we were graphing didn't get anywhere near 100%. It would make sense with the data that we had. I think the biggest number we saw yesterday was like 7.1. And maybe we go back in here and say, you know what, let's just look at this a little bit closer and make this like 10% instead, since 100 was really squishing our data down. And it looks like that. So now it's decision time. Could we fit a line to that data and would it be pretty close to all the data that we see there? Well, it would be better than a parabola, and it would be better than an S-curve, so I guess we go with linear. I mean, it maybe isn't going to be perfect, but it should be better than the other choices that we have. So we go into stats, and we go to calculate, and that's going to be linear regression. That's number 4. So put that in there, Chandler, stay with us. But now we see our lists here are not the list that we wanted. We wanted list 1 and list 4. So second, list 1, enter. Second, list 4, enter. And I'm going to store this one. I want to see it go right over the top of those points if I can. Do you remember how we get that y variable? Where did it go? How do you get y sub 1 to show up there? Bars. They're in there. Down to calculate. Now what I want to know before I go to the other screen is how good a line of estimate is this going to be? Well, if we go to 3 decimal places, it's y equals, you put the a up in there, 0.127x plus 4.078. And I see my R value is 0.987. That's pretty doggone close to 1. So it's probably not hitting every point, but it's probably pretty close. So I put in graph. Now look at that. I mean, really, it looks like there's maybe only one point that's not being touched by our line of best fit. So that's why we had such a good number. And here's what's even better. Press y equals. I didn't want to have it in all of decimals. I was going to go 3. But the calculator stores all of that in there for us. So we get that decimal equivalent. It actually goes to 10 decimal places, which we would not do by hand. Couldn't hear you, Ken. Yes. On the yellow ones, what do you have though? What do you give you? You do. Okay, good. Because you can do linear regression, L1, comma, L4, comma, variables, arrow to the right for y variables, number 1 function, and choose y sub 1. And it should do exactly the same thing. It just has to be typed in more like a computer program than the new ones. Yeah. So we can get them to do that. All right, so that's our linear regression. We probably better write that down because it says, what pattern do you see? Well, it appeared to be linear. Oh gosh, what did we do? Like -5 to 30. And then 0 to 10 gave us a pretty good look. And this appears linear. And I ignored this. Here's why. You guys know how to do point slope form already. We just put the test on there. You're perfectly fine with that. So I would rather we use the linear regression at this point and got used to doing that. So y equals 0.127 x plus 4.078. Now, if we did this by hand, we would get a pretty decent model. I mean, especially if we use, like, you'll notice this was the first x point that was on here, and this is the last x point that was on there, because you always want to pick one from either end of the line to get a good line of best fit. But we certainly could, if we were forced to do this by hand, we could put it into point slope formula, and we could find it. The fact is that most businesses that are trying to follow trends, they actually have software that's going to be a lot like what we're doing with our graphic calculator. Really, almost nobody does any of this like that. There are all kinds of software pieces that they can use to get those because they want to make good predictions too, and they'd like them to be more accurate. So that's line of best fit, linear regression. We did quadratic regression and linear regression. So the exploration here says the parabola in example 4 arose from the law of physics that governs falling objects, which should inspire more confidence than the linear model in example 5. But that's because of the data. You know, the data that they had can be recreated very easily. It's not like the prison population where if you go to the next year, things might change. It's very stable, very stable. We can repeat Galileo's experiment many times with differently sloped ramps, with different units of measurements, and even on different planets, and a quadratic model will fit it every time. The purpose of this exploration is to think more deeply about the linear model in the prison example. So when we did that, was that a good model? Was that the way to go? It says the linear model we found will not continue to predict the percentage of female prisoners in the United States indefinitely. Why must it eventually fail? We just got the line. Lines go on everywhere. It goes past 100%. Exactly. Our model would pass up 100%. So that would mean all the females are going to be in prison. And then they're going to find some female aliens and put them in prison as well. And so anything female is going to, maybe animals will go to prison. No, it can't work that way. So do you think that our linear model would give an accurate estimate of the percentage of female prisoners in the United States in 2009? Why or why not? When we look at data and we use it for the years that are already in the table, that's called interpolation, and that's good because the data is already collected, and making a prediction is a very safe thing to do. But once we start talking about data, let's say our data is from the 2000s, and we want to know about 2050, that's called extrapolation. And a lot can happen from 2000 to year that we wish to find out about is pretty close to the data in the table, then usually we're okay. So if we flip back to that table, the last year that we had for data was 2005. What do you think? 2009, should we be okay? Yeah, it's pretty close. So yes, we should be able to because it's still pretty close to the model data. Yes, the year is close to the model data. It would still be called extrapolation. I suppose I should put that word down. Because it is outside the data that was collected. But it's so close to it that, if we definitely would use it. We would say that's a pretty reliable way to go. Again, the other fancy word for using inside would be interpolation. Did any of you take Providence Stats? You guys were pushed ahead. Did any of you take the course for a half a year called Providence Stats? Okay, so a couple people did. So this should sound familiar to you. And anybody that maybe has taken AP Stats already, then you definitely talked about interpolation. But interpolation is good. You can rely on that data. It's already been collected. Extrapolation, you have to be careful. How far out in advance are you trying to do this? And now, one of my least favorite pages. Oh, good. It's not the one with all the words yet. Words don't need math doesn't need all those words. What we need is numbers. So here's what we're going to do. We're going to combine some methods. This says we're going to find all the real numbers x for which 6x cubed equals 11x squared plus 10x. All right. Solve algebraically. We're just starting to move things over. I can't do that yet. What's the first way we try to find the zeros? Factor, if we can. So we need to set this equal to 0. And we need to see if it's possible for us to factor this mess. So, you see anything we could pull out all of those? Okay. Yeah, well, let's take an x. Now we got ourselves a pretty ugly trinomial there for factoring. The 6 in the front is definitely not a perfect square. We know that there are various quantities to multiply to 6. So we've got 1 and 6, 6 and 1, 2 and 3, 3 and 2. But in the back, negative 10 doesn't have a whole lot of factors. I mean, we've got a negative 1 and a positive 10, a positive 1 and a negative 10, a negative 2 and a positive 5, a positive 2, and a negative 5. So we start thinking about combinations here. I don't think the negative 1 and 10 are going to do it. So let me know when you find it. 3, 2, 2 and negative 5, right down there, wide open spaces, negative 15 plus 4, there it is. So we would have 3, 2, first and first, last and last. Get the zeros. So this would be x equals negative 2/3 when you set it equal to 0. And this would be x equals 5 halves. Now, I would rather not put this in a calculator to figure out what it looks like. I mean, I know it says verify graphically, and in the end, we certainly can. But I think we can know what this is going to look like without. Did I write something down now? That's the next thing I'm going to talk to you about. Because what's the degree of this polynomial? Degree 3. So how many zeros do we want to find? We want to find 3. So now that we know the degree is 3, can you tell me what this is going to look like? It has to be an S-curve. Now we know more than that. We know when it's going to cross the x-axis. So let's get these on here. Negative 2/3, 2 1/2, and 0. Is this a flipped around cubic, or is this a normalized curve? No negative in front, right? So it should be normal. So I'm just going to take a guess at this. I'm thinking it's going to come up like this. And do that. Because that's what a cubic would have to do in order to have those 3 zeros that we see there. And then I grab my graphic calculator. Really, all I need to know is how high does this go and how low does this go. And the rest of it, we know what it's supposed to look like. So we will turn the stat plots off. Second, stat plots. And number 4 down here takes care of all of that. So if you hit number 4 and enter, that'll turn all the stat plots off. We go into y equals and clear that little bugger out and put in our 6x cubed minus 11x squared and then plus 10x. And we'll zoom 6, because we're graphing from negative 10 to 10. Uh-oh, did it not take something I punched in? 6x cubed minus 11x squared. Rats. There. How do we figure out where that highest point is and where that lowest point is so we can be a little bit more accurate with our graph? We got a little maximum going here at the top of this hill. So about 0.358, 1.895. Almost 2. Oh, that's pretty close up here. That's not too bad. But the problem is we can't see that minimum, so we're going to have to change our y's and get a little bit lower. And I'll try negative 20. Just right down there at the bottom. Trace, we're looking for a min. Uh-oh, I better let you guys do this one. This is going to take all, oh, it's not bad. I thought it would take all maybe like 20 or anything. So 1.575, yeah, maybe 19 and a half or so. So what we might want to do with that is just make it drop down and then leave them with. Otherwise, we have to change our scale at this point. What was it? 2.95. Verify that graphic. But again, I would love to tell you by the end of the year that we won't need the graphic calculator to graph this at all, but I can't tell you that because in order to find this local max and this local min, you have to be able to do calculus. So you have to wait one more year before you can graph something like this totally without a graphic calculator at all. So we've got another one down here, but I better check the time because these calculators have to. Wow, we're doing great for time. Excellent. That is pretty rare. Let's give this one a try. Now what? moving around all over, okay? Then what? We should try and factor. Yeah, I mean, we're not guaranteed factoring is always going to work, but we should try. So, no greatest common factor, not a perfect square. I can see that with a negative 10. Two numbers that multiply to negative 10 and add to 4. Not going to happen, right? How do we get it? Complete the square. Alrighty. These are nice numbers, though. These are nice numbers. When our b value is even, it works out really slick. So if b is 4, tell me what's going to have to go in these slots on both sides. Plus 4 on both sides. b over 2 squared. See, this wasn't that bad. It's not. So what do we write in our parentheses? X plus 2. Then what do? Square root. And finally, subtract 2. But if we're going to graph that, we need to know what those are. So I'm going to take me 2 on up here. You guys find them. What are 3 decimal places? Negative 2 plus the square root of 14 and negative 2 minus. Thank you. Anybody do the negative one there?
Negative 5.742.
Is that it for zeros? How do we know we found them all? Degree 2. Okay. So 1.742 up there. 1, 2, 3, 4, 5 and change right there. Well, what does something like this look like? X squared plus 4x minus 10. Which way is it open? Up? Okay. So we're saying we're pretty solid with our thought. It's going to look something like that, right? Well, we better get the graphic calculator because there's one thing we need to know. We need to know how far down, how low does it go? That's what we need. I have to keep the 0 again. The ordering machine doesn't like it when I record. It's going to put 0. Might go past our 10. Once you find this, how low is that going? Note down there, aren't we? Now, if this is a test, I don't do that. I don't go off the grid. If this is a test, I relabel it and go by 2s so I can fit it on there. Because in a test, we want to see everything in great detail. Now, could we have found that without the graphic calculator? Yes, because this is a parabola. And way back when, many, many years ago, you learned this little formula right there to find the x-coordinate of the vertex. So we could have gone here and said, okay, I need negative 4 divided by 2 times 1. Hey, that's negative 2. And then we could put negative 2 back in here and find that algebraically as well. So with the parabola, we can find the lowest point in because it's the word text, but not with the cubics. Gotta trust the calculator a bit for that. So this says, while the decimal answers are certainly accurate enough for all practical purposes, it is important to note that only the expressions found by the quadratic formula, those words, by completing the square, give the exact real number answers. The tidiness of exact answers is a worthy mathematical goal, always, when having exact answers. Realistically, however, exact answers are often impossible to obtain, even with the most sophisticated mathematical tools. So, in the end, sometimes we use the old decimal equivalents here. My least favorite page. Every method of solving an equation usually comes down to finding where an expression equals zero. So we try factoring, and factoring doesn't work. It depends on, is it a quadratic? Because if it's a quadratic, we should complete the square. But if it's a cubic or a quartic, we're probably going to have to graph the bracket. So if we use f of x to denote an algebraic expression in the variable x, then here are our connections. Well, we've already talked about how the zeros are also called the solutions. Because we've been completing the square, hopefully we can see the connection to being called a root. If every quadratic can be solved by completing the square, then when you take the root, you really are finding those zeros. So if a is a real number that solves the equation f of x equals 0, then these three statements are equivalent. It's the root, it's the solution of the equation. It's the zero. The number a is the x-intercept of the graph. So we're putting that all together. What do we see when all this is together? So sometimes the point A0 is referred to as the x-intercept. Usually that's a good graph. You want to find out where it's crossing. Note, functions, two variable functions have zeros. One variable equations have roots. Yeah, I don't know. We use those kind of interchangeably. The book's being a little picky here. That if we have x's and y's, we should call them zeros. But if we just have an x, we should call it a root. It depends on how you're solving that problem. It really does. I mean, we're not going to worry about the vocabulary. We want to be able to do this. So now, what if we get monster word problems? Well, they're trying to help us out here with some tactics that we can use to understand the problem. Read the problem as stated several times if necessary. Find a starting place. What grabs you? Be sure you understand the meaning of each term used, because often that will mess up labels and things if you don't understand what it is you're looking for. Restate the problem in your own words. Discuss the problem with others if you can. Yeah, you're stuck, email me, email somebody, call somebody and say, how'd you start this? Identify clearly the information that you need to solve the problem. You have all the information that you need. Find the information you need from the given data. Sometimes, when we were first working on baby word problems, and they did that instead of that, sometimes you get tripped up. Not anymore, but it used to happen. You'd be looking around for a number, and because it was a word, it would throw you off. Develop a mathematical model of the problem. So draw a picture to visualize that problem situation. It really helps. Introduce a variable to represent the quantity you seek. What are you looking for? Make it x. Whatever. Usually with the word problem, we'll try to connect it to what it is we're looking for somehow. If you're looking for cost, maybe you'll get a C. And in some cases, there may be more than one. Use the statement of the problem to find an equation or inequality that relates the variables you seek to quantities that you know. Connect it to something that you already have achieved. Solve the mathematical model and support or confirm the statement. So solve algebraically using traditional algebraic methods and support graphically or support numerically using the graphing utility. Remember, we're supporting our answers with the graphing calculator. They are not how we're getting them. We would rather have everything algebraic. Solve graphically or numerically using the graphing utility and confirm algebraically using traditional algebraic methods. Check your answer. So that's it. Fancy words. Check your answer. Solve graphically or numerically because there's no other way possible. Cubics, quadratics, we've tried everything we possibly can and we can't get them. We're going to graph the graphing calculator. Then, put in the words what you find. Translate your mathematical result into the problem setting and decide whether the result makes sense. is your answer ridiculous to the situation? You just did a problem about money and you came up with negative $12.45. No, no. Think about that answer. What does that mean? So on the next page, we're going to start with a little baby word problem here, applying the problem-solving process. And it says, the engineers at an auto manufacturer pay students 8 cents per mile plus $25 per day to road test their vehicles. How much did the auto manufacturer pay Sally to drive 440 miles in one day? Well, the way that I always approach word problems is not the way that they have them. Because what I do is I look for totals, and then I figure out how do you get that total and go from there. So when they said, how much did they pay Sally to drive 440 miles, I latched onto that right away. And I thought, there's a total, 440. Well, if that's the money that she gets paid, I need to have a place to put that. So I go back up to this problem and it says the engineers at an auto manufacturer pay students 8 cents per mile and 25 cents per day. Well, they said she was only driving for one day. Right there. So they must have paid her $25 because it says right there they get $25 per day. But that wasn't all they paid her. What else did they pay her? They paid her 8 cents a mile. So, how much did they pay her? Well, what I have to do is figure out where that 440 goes. And because it's 8 cents a mile, I'm going to go ahead and go with M per mile there. Well, that's the formula I should use. That total of 440 actually has to go in there so I can see how much did they pay her. Now, if we go according to the book, then we do it this way. We'd say, it says identify the variables. So things we don't know. We don't know how many miles when they give us this original model. And we can just make that happen. Express all unknown quantities in terms of that variable. Well, that's what this was. 25 plus 0.08. Yeah. Set up the model. All right. It really should be an equation. We should have it equal to something. So we think, well, what would they call this? It is how much they're paying her. So maybe P for payment, C for cost, because it's a cost for them. So either way, we'll get there. And what we know is we want to find how much Sally got paid. And we know how many miles. So $25 plus 8 cents a mile for 440 miles. How much did she make? 60.2, so $60 and 20 cents. So she, one day, took one of their vehicles, went and drove around with it to whatever testing area they wanted her to, and she went 440 miles and she made $60.20. 440 miles. Well, not a bad day's work, I suppose, if you just drive them. Then, he says, John earned $93 test driving a new car in one day. That's good, because all the rest of this is in one day. How far did he drive? Well, don't we have a spot where we could put the money? I mean, this was just the money right here. All right. So let's put the money in there and work backwards. Let me know when you've got that one. Subtracting 25 divided by 0.4. So how many miles for, what was the guy's name? John. 850 miles. 850 miles. So it says support graphically. Oh, that's a little silly because with this especially, it was so easy to get our algebraic equations. But if we wanted to support this graphically, well, we would just graph our 25 plus 0.08x, and we would see what it looks like. We should not be shocked that it's a line. We should. And then we could just use our trace button to get to the 440, or we could set our table so we could see the 440, and we should be able to see that 60. Why that? A little bit different over here, because if we were going to solve this one with the calculator, we would probably do the old y sub 1 and y sub 2 with that one and look for the intersection. The book goes after it a different way. And what they say is, all right, you've still got this line in there, so what we need you to do is go over here and find out when y is 93, and then you can just cross-reference what that is in the table and work with that. That's easy. And the last step is tell somebody what did you find when you did this problem. And for A, it was how much did the auto manufacturer pay Sally to drive 440 miles in a day. So we would want to say something like Sally earned a total of $60.20 for driving 440 miles. Just kind of put it all together. You know? So if somebody just takes a quick glance at our map, doesn't really read the initial problem, this, oh, look what they were trying to find. They were trying to find how much Sally earned. She drove 440 miles. So what's something we could say for John's? Because John's was, John earned $93 test driving in the car in one day. How far did he drive? Give me a sentence that rounds all that up. There we go. Just pulls it all together. Now, I hope to get to the next one because that is kind of where we were last year. But you know what? We have more than enough time on Monday to finish what we need to for this section. So, we've covered a lot of ground today on those objectives. And grab that yellow sheet I gave you yesterday. Because at this point, what I want you to do, remember you were going to rate yourself before we started. Set up models to represent real-world phenomena using numerical, algebraic, and graphical methods. We did that. We did linear regression and we did quadratic regression. So remember that 4 is, hey, I could go out and collect the data all by myself and do all of this. 3 is, give me any of the problems on the homework, I'll be able to find the linear regression. Well, kind of started this. We didn't really finish it. So maybe give yourself a before rating on combining the algebraic, graphical, and numerical methods to solve a verified solution. So rate yourself on that. And now, you definitely should be able to do day 1. And probably get a pretty good start on day 2 here. Oh, this book was one of those things where the reason they picked it was because the calculus books and every other book that you have were the Pearson books. It has typos like crazy. So that's what all of this black stuff in this is about. It's about the fact that don't use the back of the book for your answers anymore. Make sure you're using the answers that I have on Schoology.
For section 1, it says that we just want to connect with you to 37.
Go by what's up there. because after we taught it the first year, we had to change the split of things about how much time we had with each topic. And initially we had this in 2 days. There's no way to get